Okay, well, I'd like to first thank all of the TAG members for being able and willing to participate in this project and for all the support that they have given us so far. So if you're all in the call, and I think most of you are, it would be great if you can probably just give a very, very short introduction to the rest of the group. And I'll start with Jim, who I'm actually seeing right now.
Yeah.
Hi, Jim.
Hey, everybody. Yeah, this is Jim Bass with Jacobs Engineering, and I'm a subject matter expert in the design and planning of natural treatment systems, and have projects underway that resemble the ones that we're talking about here right now.
Thank you. So I guess Kim Byers not in the call.
That's correct. I'll take it. So this is Damian Trammell with Hillsborough County Solid Waste Management Division. I think that's enough. Been with the county for several years now. I look forward to kind of understanding what's going on here and how the county can work together and figure out what kind of projects going on. So.
All right. Thanks, Damian, for attending. Stephanie.
I don't think Stephanie's on the call.
Okay. All right. Well, Stephanie's with the Environment and Research Education Foundation. Bill is in the call.
Yes, Bill Cooper. I'm a photochemist and well, actually a whole bunch of different things, and a radiation chemist and a PhD in oceanography. Spent many years doing surface water chemistry and continue that. So I'm very excited to see what you're doing.
Thank you, Bill. Ashley Downley-Thompson.
Hi, I'm a professor at Florida Gulf Coast University in environmental engineering. Since the last time I talked to Sarina, I've actually been promoted to associate professor. So, but I do solid waste research and have done a little bit of wetlands research. So I'm, just excited to see what you guys are finding and what you're doing.
Excellent. Thanks, Ashley, and congratulations. Ashley Evans.
Hi, this is Ashley Evans. I'm with Waste Management, specializing in solid waste engineering through lots of different disciplines. So,
excellent. Thank you, Ashley. And Melissa?
Hi, yes. My name is Melissa Madden, and I work in the Southwest District of the Department of Environmental Protection, the regulatory agency for the state of Florida for environmental stuff. I'm a subject matter expert in solid waste. Been working for the department for about 14 years in solid waste, and primarily my role now is to train staff, but I also get to do special projects like this. So, good stuff.
Excellent. Thank you, Melissa. And last but definitely not least, Larry.
I think Larry's also not on the call.
Oh, okay. So Larry is the operations manager at the Southeast Hillsborough County landfill, where we have been doing the research. I would also like to thank Wes and John with the Hinkley Center, who have been providing a lot of support. Nestor, I think there's a lot of feedback coming from you. So also, I see that there's a lot of people that sign up for the call for this presentation. So thank you all for attending this. Next slide. Okay, so we have a lot of updates to present, which is great. We have been pretty active. We're actually going to start with a little background to kind of put us all on the same page and understand where this project started. We'll present some updates on the main research tasks that we have been working on the past few months. And then finally some of the metrics that we're accomplished so far. Okay, so what are some of the issues that we're investigating related to landfill leachate? Here in Florida, it's very common to discharge landfill leachate to publicly owned treatment works, and these kind of have issues because of the high ammonia, the recalcitrant organic matter, and metal concentrations in the leachate, which if the concentrations are too high, can completely disrupt the biological and chemical processes in charge of treating the wastewater. Because of these issues, treatment wetlands have been constructed treatment wetlands. I will probably use those terms intersexually all the time. They're ecological natural systems that have been used in the past to treat not only leachate but other types of high high strength polluted waters. So the removal of different types of pollutants in treatment wetlands have been well documented, in particular organic compounds, nutrients, nitrogen, and some trace metals. Another benefit related to treatment wetlands is that they could reduce the net volume of leachate via evapotranspiration. Because of the warm temperatures year-long here in Florida, there's actually great conditions for treatment wetlands for growth, plant growth, and also for biogeochemical processes that are in charge of treating all of the pollutants. There are many ways of designing treatment wetlands depending on a number of different design criteria. And based on previous research, it has been demonstrated that a combination, a hybrid of vertical flow wetlands with horizontal subsurface constructed wetlands will do a pretty good job of overall removing the nitrogen in leachate. So I'm not going to read through these points here, but I just want to point out that we're addressing directly 3 of the main questions from the Hinkley research agenda as of last year. Okay, so with this, I'd like to pass it to Dr. Ergas, who's going to give us an introduction and a recap of the study hypotheses and objectives.
Okay, so our guiding hypotheses for this research is that the addition of zeolite, which is a natural mineral with a high affinity for ammonia, to vertical flow constructed wetlands can reduce the free ammonia toxicity and enhance biological nitrogen removal. That the addition of biochar, which is a low-cost material, organic material produced by pyrolysis of organic feedstocks, can enhance plant growth and retain recalcitrant organic matter and enhance biodegradation. And that these adsorbent amended hybrid constructed wetlands can provide a cost-effective and low-complexity landfill leachate treatment method compared with conventional on-site leachate treatment systems. So we have 5 objectives, and we'll be going through them one by one. Mainly having the students present the results of their research. In terms of zeolite, it's a porous aluminosilicate mineral. This is a picture of a pile of zeolite. We've been using clinoptilolite, which is one of the most abundant and commonly used zeolite materials. We purchase it from a company that has mines in Utah and New Mexico. And it's widely used as a chemical sieve. It's used as a food and feed additive. And some of you may be familiar with, if you have multiple cats, you might get the odor controlling cat litter. It's a very lightweight, inexpensive material. And these are some of our preliminary batch experiments where we had an initial ammonia concentration in landfill leachate above 250 milligrams per liter. We can see that with zeolite addition, we can reduce that concentration significantly. This is just by adsorption or ion exchange. Biochar is a low-cost material. It's produced by pyrolysis of organic feedstock. The material that we're using is made from wood chips. But we also see biochar produced from things like biosolids and livestock waste. It has a very high surface area and cation exchange capacity, a good moisture holding capacity. It's been extensively studied in agriculture to improve the crop productivity by retaining nutrients and moisture and enhancing the growth of beneficial microorganisms. And again, this is some preliminary results from our lab where we carried out abiotic batch studies, and you can see the initial COD concentration up above 700 milligrams per liter, and that adsorption of COD by the biochar. So our concept here, this conceptual model for what's happening in our reactors, we add our landfill leachate. We have our adsorbent material, either the zeolite or the biochar. The compounds, let's say ammonium in the landfill leachate, are adsorbed by the adsorbent. There's an equilibrium that's reached between the liquid phase and the solid phase. But then we get the biological transformation of the compounds, which drives the desorption of them from the solid phase to the liquid phase. And so at the end of the bioregeneration step, the adsorbent is fully regenerated by the biofilm and able to adsorb more compounds that come in with the next load of leachate. So that's the conceptual model of this process. And so now I'm going to pass this on to Erica, who's going to talk a little bit about our bench scale sequencing batch biofilm reactor studies with and without adsorbents to investigate the effect of the adsorbent and aid the pilot system design.
Thank you, Dr. Ergas. So in order to test our first research objectives, we created 3 sequencing batch biofilm reactors as shown on the slide that contain either lightweight expanded clay aggregate, which is just the clay by itself, and that's the LECA plus zeolite, which is termed C and Z. And then the final SBBR is the LECA, zeolite, and biochar, which is termed CZB. At the right, we have a basic schematic for the SBBRs, and the main take-home message for how they were operated is that there was a first an anoxic stage, following that an aerobic stage, and then finally a decant stage where the effluent was released. And this was used to mimic conditions within the constructed wetlands. Below we have a table that just shows the main stages of operation. So there was a 100% recirculation period. And then after that, the reactors were operated continuously at different HRTs. Next slide, please. Okay, so this slide shows our results over time in terms of the COD removal. The red triangles represent the influent concentration. The yellow squares represent the C and Z SBBR. The gray triangles represent the clay, the LECA SBBR, and finally the blue circles represent the LECA, zeolite, and biochar. And over time, we can see that at both HRTs, either 14 days or 8.75 days, the CZB or the biochar containing SBBR actually perform best in terms of removing COD. Now, when we looked at color removal, again, the biochar containing SBBR performed the best in removing the most color. So this was pretty exciting. Not only were we seeing COD removal, but also color removal was being observed in the SBBR containing biochar, confirming our hypothesis. And then finally, in terms of ammonium removal, all three SBBRs achieved ammonium removal at both HRTs. So finally, when we looked at NOx removal at the higher HRT, all three SBBRs achieved high ammonium removal. However, at the shorter HRT, the biochar containing SBBR didn't perform as well. And this is possibly due to organic carbon limitations that may have prevented denitrification from taking place. So we continue running the CZB bioreactor for over a year. And this slide highlights the snapshot of the nitrogen species that we recently measured. And as we can see that over time, in terms of the total organic nitrogen removal, in terms of the total nitrogen removal over time, we observed a high removal of this, possibly due to anammox activity that was occurring in the reactor. And so I'd like to pass the presentation off to Shia, who will be discussing the pilot scale study of our research.
Thank you, Erica. So the Hillsborough County's Southeast landfill has a Class 1 landfill with tire processing facility, composting facility, and an on-site leachate treatment facility. So a portion of the leachate is treated on-site by the leachate treatment facility in the landfill, which is an activated sludge biological nitrogen removal system with glacial addition as carbon source. The additional leachate and then effluent from the treatment facility is hauled to the county POTW. So our pilot scale constructed wetlands are located in the area adjacent to the treatment facility in landfill. The county is very interested in the potential implementation at adjacent wetlands. And then the operators there are also very enthusiastic collaborating with us for this project. And then they really provide a lot of help when we built the systems before. So we have two pilot scale hybrid vertical flow and horizontal flow constructed wetlands side by side. So the system 1, we put gravel in both vertical flow and horizontal flow tanks, which is our control system. And then system 2, we add zeolite in vertical flow tank and biochar in horizontal flow tank. So for both systems, we feed with the raw leachate. And on the right hand, here are the pictures of different media we are using. And then we will plant the low cost, low maintenance leachate tolerant plants, cattail and cordgrass into our system. So the diagram is the whole flow chart of the wetlands we built in landfill. So we have the storage tank first, and then we pump the leachate from the storage tank to vertical flow tank first. We have the distribution pipes on the top to distribute the influent evenly, and then the effluent will flow to the horizontal flow tanks by gravity. And then the final effluent will be collected in the effluent tank and then be pumped back to a pump station to wastewater treatment plants. We collect the samples after vertical flow tank and also horizontal flow tank. So the bottom left corner is the picture of the real wetlands we built. Here are two photos when we built the wetlands. In the startup period, we seeded the wetlands with sludge from the onsite leachate treatment reactors. So to avoid the shock loading to microbes, we increased the leachate percentage in influent gradually. For example, 25% in the beginning, and then increase it to 50% until 100%. So now we already added 75% leachate. So this step is almost done. And then we will plant the cacti and cordgrass soon. So we monitor pH, alkalinity, TSS, VSS, nitrogen species, soluble COD, BOD5, UV adsorbents, and even heavy metals in the future. The level log sensors were set up for water level, temperature, and conductivity measurements every 10 minutes. Here is a picture of ammonia analyzer and level log sensors we are using. Here is the preliminary results in the startup period. So the figures in the left side is from the vertical flow tank. The right side is from the horizontal flow tank. The G means gravel tank, gravel system or control system. GZB means gravel plus zeolite plus biochar wetlands. So I added 25% leachate in the beginning on day 0, and then 25% leachate on day 17th, and then another 25% leachate on day 28th. So for pH, there is no significant difference between G and GZB in vertical flow tank and also horizontal flow tank. So the pH numbers are all in the healthy range. So for alkalinity, the alkalinity concentration in J and GZB are also pretty close to each other. COD concentration, so we can see the orange dots, the GZB has a lower COD concentration. So the biochar in GZB achieved higher COD removal than G, and the same results can be found in UV 254 figures. So biochar addition in GZB can remove the color and also organic matter effectively. And on the top figures, the effluent from GZB is clearer than raw leachate and G. Ammonia and nitrogen. So we can see the orange dots, the GZB has a lower ammonia nitrogen concentration. So because we have zeolite in GZB, zeolite absorbed ammonia to reduce its concentration. We can also see the figures of free ammonia at the bottom. The GZB has a lower free ammonia concentration too. So the zeolite in GZB absorbed the ammonia to reduce its toxicity to nitrifiers. So we can see the effluent in GZB is lower than 10 ppm, which is the inhibition concentration to nitrifiers, so which confirmed our hypothesis before. NOx concentration. So we can see, especially for GZB, there is a slight NOx accumulation. We can see next slide for the nitrogen balance further. So here is the nitrogen species balance for J and GZB. So we can see the GZB wetlands achieved higher total nitrogen removal, and also the ammonia concentration in GZB effluent is much lower. So the GZB has better nitrification performance, but there is a nitrate accumulation in GZB, which is due to the limited carbon source. The connectivity, so connectivity of landfill leachate is around 30% of the seawater, so it's very high. Even after J and GZB, the conductivity concentration in J and GZB are still very high, so which needs further removal. So now we will shift to Lily to introduce developing a numerical process model to predict the performance of the hybrid constructive wetlands under varying operational and leachate characteristics. Thank you.
Thank you, Shia. So like she said, we are creating a numerical process model that is being coded in Python. So here we have a conceptual model that describes all the processes that typically happen in the wetland and what we're keeping track of. So We're keeping track of ammonia, organic nitrogen, and nitrate, as well as oxygen and COD. So the diagram shows ammonia is converted to nitrate through nitrification, and then nitrate converted to nitrogen gas through the denitrification process, which requires an organic carbon source. And then denitrification also requires an anoxic condition. So for the model, we're keeping track of dissolved oxygen concentrations. And here we have some preliminary results from running some simple numbers through the model that we have so far. So I have mass balance equations for organic nitrogen, ammonia, and nitrate. It's currently being modeled as a completely mixed flow reactor. And for simplicity, the flow rates of leachate is considered steady. So we can see small organic nitrogen removal rates, higher ammonia removal rates, and then we also can observe nitrate accumulation, which would indicate that there are higher rates of nitrification than denitrification. So for now, I've used constant rates for nitrification and denitrification from literature. And then we're gonna start putting in the actual data from our pilot study into the model, and then we'll be able to calibrate the rates of nitrification and denitrification. And then next, Lena will talk about the enhanced leachate denitrification in constructed wetlands using iron sulfur minerals.
Dr. Ergas, did you want me to go over this?
Yes, either you or Erica could just briefly mention what you're doing.
All right, so as we saw from the SBBR, ammonium was being removed, but at the last step of the process, after the aerobic step, we noticed that the nitrate concentrations were above 200 milligrams per liter in the effluent. So we decided to start investigating ways to use another project we've been working on, which involves iron sulfur minerals, to facilitate autotrophic denitrification to remove that nitrate. So we've been currently testing sphalerite, which are pictured in these microcosms down on the left. We have two versions. We have an abiotic and then a regular control. So the regular control has the sulfur minerals and oyster shells, and the uninoculated has the oyster shells and the sulfur, but without the microbes. And the reason we're using oyster shells is because we've seen high nitrate removal efficiency in previous research done in our lab. And then we have some preliminary results for these studies, but we will wait till the next report to present on them.
So now we go to Misty.
Hi guys. So I'm going to be going over our preliminary assessment of post-treatment requirements. So we have the water reuse potential here. We compared water quality parameters of the landfill leachate and the sorry, you can hear my boyfriend in the back. The batch reactor effluent against agricultural and industrial reuse standards. The effluent from the SBBR reactor with the additions of the zeolite and biochar primarily fall under the reuse standards for BOD and total nitrogen. However, conductivity is of concern, as you guys can see in the middle chart. And the data for the heavy metals removal is very preliminary at this stage. Looking specifically at conductivity, in prior studies, we assessed or read through constructed wetlands were an excellent pre-treatment for ultrafiltration and reverse osmosis processes, as well as membrane fouling and energy cost. The combined use of constructed wetlands, ultrafiltration, and reverse osmosis resulted in a high conductivity removal efficiency that is greater than 98%.
So our next steps, we're continuing to run the bench and pilot scale experiments. So as you saw, we were initially running 3 bench scale studies. Now we're just continuing with that CZB, looking at the long-term performance, as well as doing the microcosm studies with the iron sulfur minerals. In terms of the pilot reactor, it's still in a startup phase. We'll be shifting to 100% leachate soon, and then adding the cattails and cordgrass to the pilot. In terms of the I guess we don't have anything here, but the other part of the project is the mathematical modeling. So that's also continuing. And then Misty is working on the reverse osmosis analysis, doing some simulations of the RO system using wave design software by DuPont Water Solutions, and then estimating the capital and O&M costs. I just wanted to mention here that we did have some setbacks due to COVID, some time when we had to kind of shut down things in the laboratory and then regroup, and some delays in terms of, supply chain issues, getting the tanks, for example, for the pilot reactors, getting PPE for our students, getting authorization to travel for our students. So we are going to be operating on a no-cost extension pretty soon. The practical end benefits for end users, this from the proposal, they're low complexity, low capital and O&M costs, proven long-term performance for removal of organic matter, nutrients, and metals from landfill leachate. The low-cost adsorption materials, adsorbent materials can reduce the land requirements and improve effluent quality. And the effluents could either be safely discharged to POTWs or treated further to meet reclaimed water standards. Here's our team. As Mauricio mentioned, we've already had 2 master students, Alex and Bisheng, who've graduated. We also have Bisheng's thesis. We submitted an abstract to the American Ecological Engineering Society annual meeting, which was accepted, but then the conference was canceled. So we hope that we'll be able to present that in the future. And Bisheng has a manuscript in preparation that we've been working diligently on, and we should be able to submit that soon. In terms of leveraging funding, Erica has some funding from the Sloan University Center of Exemplary Mentoring, as well as the McKnight Fellowship. Lena is now partially supported by a College of Engineering REU program. And Lily and Misty have funding from an NSF STEM scholarship program focused on managing the nitrogen cycle. And so that's our presentation, and we encourage you to give us feedback and any questions that you might have.
Yeah, that's great stuff, Sarina and everybody. This is Jim. I really appreciate the work you've done, and I like the integrated aspect of the project. You're looking at multiple important features at once. I had a couple of questions along the way, if I could ask, to different speakers. And I think if I could just start with Shia. Good to meet you.
Yeah.
I wanted to ask you about the vertical flow design here. 2 things about that. What we have learned from working with Zeolite is the importance of washing that material before you install it. It tends to have a lot of fine particles attached to it. And I'm wanting just a question, just making sure that that's what you did when you built your reactors. Is that correct?
Yeah, so we wash the zeolite in the lab and bring them to the landfill.
Okay, all right. So do you have a grain size distribution of the material that you've been placed into the reactor?
Yes, I have. The zeolite is kind of smaller. The particle size is around 1 millimeter. So it's very small.
Small, yeah. Okay, good. So you have that. That's what I'm really just confirming, because it will have an impact on the hydraulic conductivity of the material when it's fully grown in. The other thing I wanted to ask you about is the mechanism of flow application to your vertical flow reactor. How is that flow being distributed? And is it continuous, or is it a periodic dosing? I'm sorry if I missed that in your presentation.
It's okay. So for the vertical flow, we have the pump before the vertical flow tank. So it's not continuous, it's intermittently. So we will use the pump to pump the influence from the storage tank to the vertical flow tank, because there is a flow rate. So it's not very slow. So there is a kind of pressure, then the water can be distributed through the distribution pipes.
And is this water being, bear with me, let me just bear down on this a little bit. Don't mean to take up all this time, but is the flow being applied from the, like an upflow and then like a fill and drain concept, or is it actually dosed across some kind of a distribution piping network?
So it's not, so we have the pipe, like we have 2 pipes. So it's not a circle distribution, but just 2 pipes in the kind of middle of the tank. And then the influent will be drained through the hose on the distribution pipes. So
Okay.
hopefully I can answer your question.
Yeah. So when you're dosing it, is the water levels accumulating and then being released, or is it pretty much the dose distributes the flow and then that trickles down through that media to an underlying collector? Is that more like it?
Yeah.
Okay. All right. This will be
Jim,
something.
I also want to mention that we have in our last last report on our website, we also have some detailed schematics of the pilot, as well as photos of the distribution system.
Oh yeah, okay, I'll catch up. Thank you. I know there's a lot of stuff there. So thank you, Shia. I'd like to, if it's possible, I'd like to see your installation, your wetland sometime. Maybe we can arrange to meet out there or something like that. That'd be okay?
Sure. Okay. Yeah, that sounds good.
Great.
Yeah. Okay, well, one last question. We'll get more, but I don't want to, obviously I'm taking up a lot of space here. For the modeling folks, I think that was that Erica that talked about that? I think.
It was Lily.
Lily, sorry. Yeah, there's a big crowd here, big team. In the model that you're looking at there, it looked like it's a fairly straightforward ammonia or nitrogen mass balance type model. 2 things about that. One, would there be the ability to model an anammox component to that? And the second, could you, do you have could we model the addition of additional oxygen or change the oxygen transfer within the system, possibly with a forced bed aeration or some other mechanism to improve the oxygen transfer? Could that be included in the model?
So your first question about anammox, I wasn't planning on modeling that into the system. I think we didn't really see high rates of that from the batch scale study from the previous design. So I wasn't taking that really into consideration. And then can you repeat your question for the oxygen?
Yeah, the actual is could we include, is the model flexible enough to add in additional oxygen as if you were aerating the system to improve the oxygen transfer?
Yeah, I think that would, I could just add different terms into my mass balance for dissolved oxygen to.
Okay, something to think
Jim,
about.
could I just ask a point of clarification on that? Was your question, this is Bill Cooper, is your question there related to the nitrification step? Is that what you're looking for, increasing the oxygen so you get faster nitrification?
Exactly. Looking at those, the residence times that were in the plots from the model outputs, those are very reasonable results, but what that will, the implication will be footprint for the system. So what we're seeing is intensifying the oxygen transfer helps reduce that footprint, not completely, but substantially. So if you just modeled it, you would get a handle on, I think, how much gain you could, how much area reduction in the wetland for the additional treatment that you get.
Right.
Okay.
Also, I wanted to point out, Jim, a couple of points. One is, with our short-term bench scale SBBR study, we really weren't seeing much anammox activity. In fact, we saw high nitrate concentrations in the effluent, possibly due to carbon limitations, as Erica said, and because the COD is very high in leachate, but the BOD is quite low, and so there's not a lot of readily bioavailable carbon. But as Erica has continued to operate the reactor over a longer period of time, which has now been more than a year, we are starting to see very good total nitrogen removal. We haven't done any like qPCR or anammox activity tests, but we do believe that that may indicate that we've had some, acclimation of anammox, because we do have good conditions during our anoxic phase. We have high ammonia concentration as well as high nitrite concentration. So we do actually believe that we're seeing anammox activity there. And then I also want to mention the role of zeolite with the intermittent dosing, because we, what we've been seeing in our other studies, I have a project where we're looking at treatment of dairy runoff. You get that adsorption during the dosing of the ammonia to the zeolite, and then after the dosing period, the wetlands, the vertical flow wetlands drained. You get an opportunity for oxygen coming in, and because you have that biofilm attached to the media and the adsorbed ammonium, you can actually get enhanced nitrification due to better conditions for nitrification. Rather than having the ammonia just pass right through, you're kind of decoupling the residence time of the ammonium and the residence time of the hydraulic residence time in the system. So I think that is another big advantage in addition to that toxicity issue.
That's good. It's good. Thank you, all of you.
I have a question, well, a couple of them are comments. When you first showed the zeolite in one of the early slides, it looked as though you invoked some magic there at the end. Way up there, yeah. Because it, yeah, there you go. I think the one with the, there you go, the one, number 11. Isn't that, yeah.
Oh, this one you mean with the conceptual model?
Yeah, and so what's interesting here is that that is the zeolite in the middle, right? And then so it adsorbs or absorbs, whichever is possible. We get equilibrium, then we get desorption, and then all of a sudden the adsorbent is clean again, and I'm not quite sure how that works. It says you got nitrification, denitrification, and biodegradation. So that's where I thought you were invoking a little bit of magic. I'm sure that's
and I think part of the problem is, this was a figure that was adapted from to try to, which initially was just showing nitrification and
Okay.
bioregeneration, and then we tried to like put in COD, and I think it got a little too busy there. So in the ion exchange process, if you can imagine, when the wastewater is added, you actually have other cations such as sodium in the landfill leachate. And so what you have is, because zeolite has a higher affinity to ammonium than sodium, what you get is an ion exchange where ammonium is exchanged with sodium that's initially on the adsorbent. And you have a certain amount of ammonium that's still in equilibrium.
Mhm.
And then what happens is that you get a oxidation of the ammonium from the liquid phase, or from inside the biofilm, by nitrifying bacteria. And what that does is it converts the ammonium to nitrite and nitrate,
Mhm.
which drives the desorption, because there's less ammonium in the liquid phase because it's been converted to nitrate. That drives more desorption from the adsorbent material,
Okay.
and that is accompanied by a adsorption or an exchange with sodium. And we actually see that in our studies, that the concentration of ammonium the concentration, of sodium will decrease in the liquid phase as the concentration of nitrate increases.
Okay.
So at the end of this process, the ammonium ions are now replaced with sodium ions, and
Right.
now we're ready for another adsorption cycle. So I can send you the original
No.
figure that shows
Yeah,
that.
I just missed the no, that's fine. That explains it. So now, are you using the zeolite mostly for your vertical, or would that also be incorporated into the horizontal flow wetlands?
Right now, so for our batch, I'm sorry, SBBR sequencing batch biofilm reactors, it was just a single reactor. So, we had this control with no adsorbent. We had the reactor with zeolite. And then, I mean, ideally we would have had, one with just biochar and then one with both together, but we had some limitations as to how many reactors we could set up in the lab. So our last one had zeolite and biochar. So this was all mixed together. When in the pilot wetlands, what we've done is we've added the zeolite only to the vertical flow wetlands to enhance nitrification, and we've added the biochar to the horizontal flow wetlands to enhance COD and color removal. So we've separated them out.
Okay. Well, so that leads me to my next question. When you've got these horizontal, so just to back up, I mean, a lot of the work I've done over the last 30 or 40 years has been in photochemistry, and what I would like to see in wetlands is some open water, so that you can take advantage of the energy from the sunlight to possibly convert COD to BOD. But I noticed in some of your, I mean, you're using cattails and you're using cordgrass as the two emergent vegetations that will be in here, which is good. And they can actually add a considerable amount of organic carbon to the water and possibly increase the photochemistry that's going on too. But it seemed to me that you're looking at these wetlands as being mostly vegetation. In other words, you're not going to have open areas. I mean, you showed one wetland which has got an open area which would have great opportunity for photochemistry, but you're not really considering that aspect of this at this point.
Pass that question to Mauricio, who's our wetlands guy.
I thought he was getting ready to say something.
Well, I think, ideally, if we had the opportunity to expand this into kind of a larger like pilot system, we will probably have some kind of, open areas both for kind of photochemistry and also for mixing.
Yeah.
But, the systems here are pretty small. So it's
Right.
just the footprint is pretty small, and we don't have enough space to have, a couple of cactus clumps and then also some open space area. So
Right.
I think that'll be for the
Yeah.
next step.
Well, that's fair enough. I mean, that was not a critical comment. It was just more of a question. I mean, I think you're getting really nice. I think it looks like to me that you're getting really nice results. So I'm really encouraged. I think it's great. So, yep, that's,
I guess,
that's for me.
yeah. Sounds like Jim would like to say something.
I just want to say that, including open zones and wetlands for hydraulic redistribution, and like you're saying, Bill, the kind of multiple kind of enhancing the degradation pathways makes a lot of sense. One challenge with these leachate wetlands is that the nitrogen, phosphorus, as much treatment as we're getting, are still pretty elevated, and will quickly generate a cover of duckweed. So it's hard to actually maintain an open, well, at least in my experience, it's been hard to maintain a continuously open wetland area.
That makes sense.
But it certainly is definitely a proven pathway for treatment.
The other thing is that one of the things that I've heard from, well, I don't know who I've heard it from, but somebody out there, the problem with getting rid of this leachate into a wastewater treatment plant is that they were afraid that it would go right straight through the treatment plant because it's mostly COD and not BOD. And then it would get out into a surface water where you would have an active photochemical zone. And then that would actually end up converting the COD to BOD. And then you'd end up having this oxygen sag, which is originally why we were concerned about lowering BOD before we discharged it. But I think that's, that's pie in the sky stuff right now. So I like what you're doing. I think it looks great to me.
Any other questions?
I had a few questions. So I'm really interested in the zeolite and this idea of the wood chips as well. So I understand the mechanisms behind the zeolite. That was a great explanation. Thank you for that. I'm curious about the loading rate, and then two, what is the lifetime that you expect for the zeolite? I'm assuming it's pretty high. With the wood chips, it seems like they're in the horizontal ones, they might be saturated. So I'm just curious, do you have an idea of how long you could run a system like this with those materials?
Well, I think the zeolite, as you mentioned, it's a natural mineral and it's bioregenerated in the process. So, in theory, you should be able to run these systems for a long time. I know we've run reactors in my lab for as long as a year and a half. So I know that's not a huge amount of time when you're talking about a bioreactor, but we didn't see any loss in adsorption capacity over that time. So that was very good. For the biochar, so that's a pyrolyzed wood chip material. So it it doesn't have any bioavailable organic carbon in it. I know that she has done some batch studies to look at whether any of the organic matter in the biochar was bioavailable. So we don't expect it to be able to break down. It's more kind of like charcoal. But we are actually seeing, and you can kind of see this in the data on the UV, but I think I don't have our most recent data up here, but you can see with the color removal, we actually are starting to see a loss in the adsorption capacity. And I think maybe Erica can bring us up to date. The color removal is not as good as it was even, this was cycle 10 or 11 here. Now she's been running this reactor for, for a year. And so she's got a lot more data showing that there's still been a loss in color removal. So it is possible that with the biochar, in particular, if you're looking for it to improve the color removal, you may have to add more periodically.
If I could just jump in for just a second, that's really interesting, because you see, when you're removing the color like that, that means you're getting what could potentially get a much higher penetration of sunlight down into your wetlands, which would mean that there are many compounds that would be absorbing. So sunlight goes down to about 300 nanometers roughly at the sea surface or land surface. So when you're measuring absorbance at 456, and you're seeing this, I mean, it looks like the penetration would be a lot higher, and there still are a lot of compounds down there that would be absorbing that you wouldn't be picking up at 456. That could be potential there for conversion of BOD or COD to BOD. So that's actually rather encouraging, that color removal. Does it look clearer to the naked eye?
Yeah, there was. I know that she included, I don't know if you can see this photo because it's up in the top right corner.
Yeah, right.
But she's got the, and it's not a great photograph, but you definitely see that, that the leachate, has a reddish brown color, and that when you have the biochar addition, that the water coming out of the reactors looks quite clear.
Be interesting to do a UV vis on that down to 200 to just see what it looks like. But
yeah, we also have done UV 254.
Yeah.
I only showed the UV what was it,
456.
Or 56, yeah. So
well, you can't do everything. No, I mean, I'm not being critical. I think it's really cool. Sorry,
I know our new faculty member, Catherine Alfredo, is planning to get us an instrument that'll allow us to do full wavelength scan. So hopefully we'll be able to do that soon.
Okay, I have to, excuse me, Sarina, I have to go. Hard stop here. It's great. Appreciate the chance. And Shia, I'm sure we'll be talking. And Sarina, we'll talk to you later, okay?
Okay, bye-bye.
Thank you.
Bye, everybody. Good job.
If I could just ask one more question.
Sure.
So I know, Dr. Ergas, you know that I've done wetlands work with the leach that I work with. It has waste to energy ash, so it's like very saline and everything dies in it, like all the plants that we grow. So I'm curious how you chose cattails and cordgrass. Like I'm just curious what that decision-making process was.
You know, we definitely read your Hinkley reports, and looked at all the results you had. We also had some, input from Jim Bays, who's done a lot of work with landfill leachate treatment. We're going to be getting the plants from Aquatic Plants of Florida, and the owner of that company, Gil, I actually worked with him on another project where we're looking at mangrove production using aquaculture wastewater. And so, everybody's got their own opinion. And, I think you may have worked with cordgrass. Is that correct? Was that one of the species that you had some success with?
Yeah, and cattails. I was just curious, because you have some things you can choose from. So I was curious.
So I think it was Gil was very adamant that that cattails not be used, that we needed salt tolerant species. And then Jim was just as adamant that cattails be used. And when we looked at the literature, including your research, we saw successful results with both of those species. So given that that's really not our area of expertise, we decided, well, let's try both and see what, that's what I do in my yard. I just plant everything.
Exactly, right? That's cool. That's great. Thank you.
I think one of the arguments, actually, when if I can comment, from looking at your report and looking at the leachate characteristics that we're dealing with, the leachate from this particular landfill is not as strong. So the water is like brackish water, but it's not like super high strength conductivity that will kill off anything but mangroves or actually your mangroves look like on the edges. Remember looking at those photos.
They fight for their lives. Yeah.
Yes. So yeah, I remember talking to Jim Bass, and he said that, I guess TIFA, they'll be, tough enough and they'll handle that. So we'll see.
Yeah, I know. I was so surprised to see like your leachate color here, because the leachate I work with is like black. I'm like, oh, I didn't even know leachate could look like that. That's incredible.
Yeah.
So, yeah, thank you. I'm excited to see your results for that. That'll be really cool.
Yeah, there certainly are a lot of emergent plants that can tolerate high salinity. I forgot. I'm trying to think of the one that we did. That we were doing some work when I was at FIU years ago with the University of Miami, looking at the formation of sulfur gases in wetlands, because a power plant wanted us to show that the wetlands were forming a lot of sulfur gases so that they could reduce they could increase their sulfur emissions. And it turns out, of course, they weren't. It was only about 5% of the sulfur. But I'm trying to think of the grass. One of them, if I think about it, I'll send you that. It's in a couple of papers that we published a long time ago. And so there's plenty of opportunity to get saline tolerant species to grow in those high salt waters. So Ashley, I see you got a cute little technician there.
Yeah, she's got like a little cash register sitting next to me. She's like working on her computer while I work on my computer.
That's great.
Yeah. Oh, I did have another question. So I know you're thinking that you're seeing anammox activity. So I was just curious if you do plan to do qPCR, some kind of testing for that to see exactly what's going on.
We actually, we're in the process of chatting with instructor at Hillsborough Community College in the biotechnology program, who has a student who is very interested in working with us. So one of the things that Erica and I are talking to her about is the possibility of doing some trying to do some molecular biology work for looking at anammox activity. So stay tuned about that. Anybody from the county? I know we've got a couple of folks. Do you see this being beneficial?
Can you hear me? Can you hear me pretty well?
Yes.
Okay, perfect. Can I get a copy of the PowerPoint presentation? Can you send that to me, please?
Yes, and this is actually also being recorded, and the slides and the recording will also be linked to our website. But I can send out the slides as well.
Okay, perfect. That'll be very helpful. I think this is, I'm actually don't work in that department, but everything sounds promising, and I'll be happy to share some of my notes with my team over here, and also on the PowerPoint presentation as well. I'll be able to go through it with them and kind of just point out some highlights of today's discussion.
Okay. Yeah, this is Ashley, and I just had some more inquisitive things, I guess, as far as knowing when you start doing the plants and some changes or things that within your actual pilot study. The first was more so on the horizontal bed. I know that when we talked initially as a TAC committee, there were some concerns of some short circuiting and some things. I know that you have, it looks like the distribution at the top where it enters, but do you have any concerns about short circuiting and water quickly going to the bottom of the bed, and any performance things that you might want to enhance before you add the plants? Because I was trying to go through and see from the slides on the left how it kind of might not have performed as well as the bench scale per se on some of the removal. So I just didn't know if you guys had thought about that, some changes that you might want to do before you continue on with the next phase, or was it not really a concern?
So, we are still in a very early startup phase. I mean, we only have about a month of data, and we haven't added the full strength leachate. Right now, it's still 75% leachate. But Shia, maybe you could talk a little, because this cutaway diagram doesn't really show how you set up the inlet to the horizontal system.
Okay, so maybe we can see the picture in the bottom left corner. So we have the outlet pipe on the vertical flow tank. Then we have the tubing connecting the outlet pipe from the vertical flow tank. And then we also have kind of distribution pipe in the beginning of the horizontal flow tank. It's can you Dr. Ergas, the cursor maybe can move to the distribution pipe. Okay.
Is that over here?
No, it's the other side. The other side. The
Oh, here. Okay.
Yeah. So we have the distribution pipe in the horizontal flow tanks too. So just connecting with the outlet pipe of the vertical flow tanks. So when the water comes from the vertical flow tank, then that will be distributed to the horizontal flow tanks.
And there's also a layer of coarser gravel, right, in the horizontal flow wetlands before it goes into the fine gravel.
Yeah.
To help to distribute the liquid in the horizontal flow system.
True.
Okay. So yeah, I just remember that there was quite a bit of talk in there. And then I think when we had our first TAC meeting that I was on, there was also discussion of maybe being able to take some samples along the way. So it's just not one at the end, and kind of see how things are going. And that might help identify, what would be the final, like in like a large real life situation, how long would these wetlands need to be? And that kind of also goes to the vertical one. I think I don't remember what it said exactly, but I think was it 6 millimeters of zeolite? And I didn't know if you guys had thought about, is that sufficient? Could it be increased or decreased, or just some thoughts about that layer too, as far as, you've got the horizontal, how long is the horizontal, and the vertical, how tall is the vertical?
So in terms of the internal monitoring, you can see these two monitoring wells here. So right now we're getting, we're just taking influent and effluent samples from each reactor, but we do have the ability to collect some samples from the horizontal flow wetland at different points, because we have these two monitoring wells in there.
And are those like a screened PVC?
Correct, yeah. And then Shia, maybe you can mention, you have the design of the, this is the design showing the different materials, and the 6 centimeter, the mass of zeolite that you added. What was the basis for that design?
So before building the wetlands, so we did a bench scale adsorption study for Zeolite and also Biochar. So we assume the ammonia in the influent, the concentration is around like maybe 400 or 500 ppm, and then we assume that for in the vertical tank, the nitrification time period is 2 days, and then we have the inflow numbers, maybe 80 liters per day. Based on these numbers, we calculated how much ammonia that we should adsorb by Zeolite in vertical flow tank. So, and then finally, after calculation, we need 24 liters Zeolite. So that will be 3 centimeter height of the zeolite layer. And the same method for the biochar calculation. So we also did a bench bench scale adsorption study for biochar to adsorb COD concentration. We have the initial concentration in the influent. We have the inflow 80 liters per day, and then we assume denitrification is 2 days. Then we know how much COD should be adsorbed on biochar. Then we get the volume of the biochar, and then that will be 35 centimeter height of biochar. Is that clear?
Yeah, and we applied a safety factor as well when we did that.
True. Okay.
So we basically based the amount of zeolite and biochar on our batch studies and at the loading rate.
Mm-hmm.
At this particular landfill, what's the volume that they of leachate that they produce every day? Do you know, roughly?
I remember it's like around 100,000 acres or something. It's very large.
Okay.
Luke, do you know how much leachate is discharged?
It's been highly variable because of many different changes, but I think they're somewhere around 150,000 gallons a day.
Okay. A lot of leachate. Have you got plenty of area around the landfill itself that where you can build some larger scale wetlands if this turns out to be something that's important?
Yes, we do. It's a very, very large complex.
Yes, and there's natural wetlands, right surrounding the landfill, and so there may be some opportunities to there as well.
Mm-hmm. So is it an operational or is it a closed landfill? This makes it look like it's closed, but
it's very much operational.
Very much operational.
Yeah, and it only has intermediate cover over massive portions of the site, which is why they have so much leachate generation and why it is so dilute. It's very unique. The quantities of leachate you see there.
Yeah.
Yeah, and then there's also, I know we had some issues where, the quality of the leachate changed quite rapidly when, due to runoff from the composting operations, I believe, or, rain events. So, there's quite a bit of variability as well.
Yeah. We're doing some work looking at the detailed organic chemistry of these leachates using this FTICR, that's Fourier transform ion cyclotron resonance mass spec. And we found, much to our surprise, that this leachate is the most complex solution of organic compounds that my ex-student, now associate professor, Michael Gonzier, has ever seen. We looked at some natural waters where we had about 4,000 or 5,000 different unique masses, and in an ongoing leachate we had about 8,800 different masses, and then in the closed leachate we had 9,200 different unique masses. So we're not talking about simple organic compound solutions. We're talking about probably the most complex. So, and I think maybe that's just something to remember, that we wouldn't expect one process or one system to necessarily deal with all of those organic compounds, but you've got a great start here, so yeah, keep going.
Thank you.
Sarina, I had a quick question. This is Melissa from DEP. I was just wondering if you were aware of Polk County's currently permitting. They're in the final stages of permitting a system, and they're working with Dr. Townsend at UF. And I don't know, it doesn't sound like there's a lot of overlap in the type of system that they're installing, but it is a large scale, supposed to be fully operational. So I just wasn't sure if you were aware of that.
No, I guess I visited their facility, but it was a while ago. And at that point, I think they were not doing on-site treatment, but they were piping the leachate to POTW. So be very interested to hear about what they're doing.
Yeah, so
And I
actually,
think Hernando County was also doing some constructing an on-site treatment as well. So I think it was the wastewater treatment plants don't want to take it. The landfills have had to, jump into this business.
Yep, and so we're also on the regulatory side trying to determine what the appropriate permitting mechanisms and, ensuring that, that the environment is protected, particularly the first couple of stages. The Polk County site is going to be lined. The first couple of stages are going to be double lined leachate ponds, and eventually kind of work its way through the process as it gets cleaner. So.
yeah, so that's some work that we're doing while I'm with Tim. So yeah, there's 60,000, well, if you average over the year, it's 60,000 gallons of leachate a day. Right now, they're actually spending about 20 cents a gallon to get that. They're not putting it into a POTW because it's too high in ammonia. So they actually ship it off site to an industrial wastewater treatment plant. And we're hoping and they are looking at both vertical and horizontal wetlands down there, but I'm not that familiar with that end of the system. I mean, the real engineering, I'm more interested in the chemistry that's going on.
If anyone has any additional questions, feel free to shoot them to me by email, and I will make this PowerPoint into a PDF and send it out to the tag.